The negative impact of traffic congestion on U.S. residents and the U.S. economy is well known. A conventional traffic control system includes traffic lights, detectors which are usually installed under the surface of roadways, and intersection controllers which control the operation of the traffic lights. Intersection controllers are connected to a central traffic management center. A large number of traffic signal timing systems have been deployed throughout the decades. Centralized systems do not accommodate highly dynamic traffic patterns and are not scalable. Partially decentralized systems allow intersection controllers to have some decision-making responsibilities, but network-level decisions are still made at higher levels. Fully decentralized systems mostly use dynamic programming, which severely limits their scalability. Many agent-based models have been proposed in the literature. Single-agent solutions optimize signal timing at the intersection level and do not guarantee optimizations at the network level. Multi-agent solutions make use of communication and implicit coordination, but are generally based on unrealistic assumptions. In addition, most approaches simplify the signal timing problem and were validated through simulation. To our knowledge, no published paper discusses the deployment of a collaborative multi-agent system for traffic signal timing. In this paper, we discuss the deployment of DALI, a multi-agent collaborative traffic signal timing system. Our goal is to turn existing traffic infrastructures into smart infrastructures by enhancing their digital capabilities and without investment in additional expensive equipment. We achieve this goal by plugging in smart software agents into existing intersection controllers, using existing communication links to establish communication between agents, and implementing a cooperative agent-based traffic management strategy. The DALI admin system allows traffic engineers to monitor the agent execution and analyze data through a web interface or mobile app. During the design phase of DALI, several deployment constraints had to be considered. From the traffic infrastructure's perspective, we were asked to use the infrastructure as is and not request any additional equipment such as video cameras or radars. This meant that we had to devise a purely software solution that could provide services based on basic inductive loop detectors. We were also asked to make sure that DALI would work with a variety of controllers manufactured by different companies. This meant that DALI agents had to be designed as plug-in components that interact with their controllers through well-defined interfaces. From a communication perspective, agent-to-agent and agent-to-controller communications had to use wireless broadband technologies. Finally, it was imperative that traffic safety standards be implemented at the level of commercial systems. We decided that instead of developing safety-critical features from scratch, we will use the full capabilities and safety features integrated in existing controllers. In other words, in case of an abnormal situation such as a loss of communication, severe weather conditions, or the arrival of emergency vehicles, a DALI agent will release its control of the intersection back to the original controller, which will execute its integrated safety feature. In the DALI strategy, agents continuously communicate with one another to exchange traffic information. In order to illustrate collaboration in a non-congested scenario, we consider three consecutive unidirectional road segments R1, R2, and R3, controlled respectively by agents C1, C2, and C3. By default, C2 exchanges two sets of information with C3. The vehicles detected by road segment R2's detectors, and for each vehicle is estimated arrival time at road segment's R3 stop bar. The anticipated vehicles to arrive at R3 stop bar from intersection 2 and from any other intersection preceding it up to a maximum estimated arrival time of 4 minutes, and the estimated arrival time of these vehicles at R3 stop bar based on C2's current timing plan. As the exchange of information takes place, Agent C2 continuously defines possible timing plans based on current traffic flow rate, the status of its phases, and timing constraints such as minimum and maximum green and yellow and red clearance intervals. A timing plan includes a sequence of phase combinations as well as a split and offset. Given that the agent's goal is to find the values of the offset and split that minimize delay, for each timing plan, it computes the estimated delay using the phase's estimated queue length, the estimated vehicle arrivals, and historical data. It then prioritizes the plan based on minimum delay, executes the plan with the highest priority, and restarts the process immediately. In a congested scenario, when an agent detects congestion, it deliberates and computes a timing plan that will alleviate congestion at its intersection. It then sends requests for plan evaluation to the neighboring agents that may be affected by the new timing. They in turn communicate with those agents that may be affected, and the process continues until all potentially affected intersections are informed of the plan evaluation request. Then, each farthest affected agent determines its level of agreement with the new timing plan and sends its level of agreement to the requesting agent, which incorporates it in the computation of its own level of agreement. The backward propagation continues until the initiating agent receives the feedback from the immediate agents. The initiating agent then deliberates and decides whether to execute or ignore the plan based on the received feedback. These intersections are managed by controllers manufactured by Interlight. The DALI agents are implemented in Java and run on PCs from our lab. They connect to that controller's web server through VPN and take control by changing the controller's configuration. This video shows DALI agents execution. Unlike the conventional traffic control system, which executes timing plans in isolation, a DALI agent incorporates information received from neighboring agents into its decision making. This allows the traffic to flow smoothly across intersections. An initial analysis of traffic on the Waterview corridor showed that overall, traffic variations occur during the time intervals shown in this figure. Therefore, in addition to weekdays and weekends, we considered peak hours, off-peak hours, and nighttime intervals. This figure shows the average reduction in delay for different time periods. We notice that there is a high reduction in delay for weekday nighttime, weekend peak and off-peak, and weekend nighttime. This is explained by the fact that during nighttime, on weekdays and weekends, traffic is very slow and there are only very few requests for green signals at the intersections. In DALI mode, given that the agents can predict the arrival of vehicles, they schedule green signals before the vehicles arrive at the intersection. This figure also shows that the lowest reduction in delay happens for weekday off-peak hours. The 12.81% difference between weekday peak hours and weekday off-peak hours is due to the fact that during peak hours, intersections are likely to be congested and the agent collaboration process is superior to the SCATS-R timing strategy. During off-peak hours, the number of vehicles, although high, does not lead to congestion. Therefore, agents are unlikely to collaborate and their performance is not as superior. The deployment of DALI is the result of a collaboration between university researchers and a municipality. The collaboration resulted in valuable lessons. Transitioning from the lab to the real world required 2 years of interactions with various stakeholders. The deployment of DALI required that the DALI model and agent algorithms be validated by traffic engineers, a full replica of the city of Richardson's traffic network be created in a simulation model for review by the director of the transportation department, extensive simulations be conducted based on historical data and presented to the city manager, controllers in the field be integrated in the simulation model, and extensive testing be done in a hybrid simulation setting with results presented to the city council. As researchers, we often simplify the traffic signal timing problem and make unrealistic assumptions. We learned that before developing solutions, it is critical for researchers to gain knowledge in the theory of traffic signal timing. In addition, it is also necessary to learn about the technology used in the development of commercial intersection controllers. Finally, we learned to expect the unexpected. Although most unusual deployment issues were discussed during the initial development phases of DALI, many were discovered during deployment and required architecture and code updates. In conclusion, DALI is a plug-in, agent-based collaborative traffic control system. It was thoroughly validated and verified through agent-based and hybrid simulations, and its deployment on 3 intersections in the city of Richardson showed a 40% average reduction in delay. With a demonstrated success in the initial deployment phase, the city of Richardson has agreed to expand the deployment of DALI in phase 2.